This video is on section 8.1 notes, systems of linear equations in two variables. So before we really get started on examples, I'm going to go through several vocabulary terms that are important for this section. First is to define what a system of equations is, or in this case, linear equations specifically. So a system of equations is any collection of two or more equations. For this set of notes, we're going to talk about linear equations, and typically we'll deal with only two linear equations when we're talking about two variables, but we could deal with three, we could deal with 27, although honestly that's never going to happen. The set of solutions of a system of equations is the set of all ordered pairs. Set of all ordered pairs, so x comma y, the set of all ordered pairs that satisfy both equations in the system, so they're going to make both equations in the system true. A consistent system is a system of equations that has at least one solution. That means you have two lines that cross, and they cross at one point. An inconsistent system is a system of equations that has no solutions. So no solutions would mean that your two equations or your more than two equations are parallel to each other, so they don't cross at all. An independent system is a consistent system of equations that has exactly one solution. So this seems redundant. It seems like, well, we already said a consistent system is a system of equations that has at least one solution, but this is saying it only has one solution. So there is another possibility, and that is that the two lines, instead of just crossing each other at one point, exactly one point, would be an independent system that is consistent. A consistent system could also be lines that are directly on top of each other. And so that would be at least one solution, but it would be more than one solution. And that's what a dependent system is. It's a consistent system because it has at least one solution, but it's a system of equations that has infinitely many solutions. And there are infinitely many solutions because the entire line is just solution after solution after solution after solution, because every single point that's next to the next point, all of them are solutions. They make both lines true if both lines are the same equation, basically. So we're going to go through and we're going to see some examples of these situations. And I'll be honest, these two definitions you really need to know. These ones, I had never seen these words before I started teaching, which means I made it through a lot of schooling without knowing these vocabulary terms. So these are kind of, they're good. You can have them on here and kind of look at the definitions and we'll recognize which is which. But I'm not really as concerned with the student being able to memorize the difference between these and recognize them. I'm more concerned that in a problem, in an individual problem, you could tell me it has a solution, it has no solution, it has infinitely many solutions. I'm less concerned about the jargon here and more concerned that you can actually see it on a graph. Okay, so there's a few different ways that we know to solve systems of equations, and the first is just by graphing them. This is probably the most concrete way to see the solution to a system. So it says solve each system by graphing, and then we're going to use those different vocabulary terms to describe what we see. So both of these are given in standard form, and so I'm going to go ahead and isolate y so that I can write it in y equals mx plus b to make it the most comfortable to graph for most students. So I'm going to take the x term and subtract it away from the y. 2y equals negative x plus 6. And then to isolate the y, I'm going to divide by 2. I'm going to make sure I divide by 2 with each term in the equation. So y equals negative 1/2 x plus 3, which means that this first equation has a y-intercept of 3, and then it's going to go down 1, right 2, down 1, right 2. And whenever I graph linear equations, I always say that the slope tells me to go up to the right or down to the right, and that way I can make sure that I am drawing my positive or negative slopes correctly. And then if I've run out of space to the right, then I'll go to the left in the other direction, just following that same pattern. And this would have been easier with a straight edge, but I don't have one handy, so my line is a little bit sketched out instead of perfectly straight. Okay, so here's my other equation. 2x minus y equals negative 8. I'm going to take the 2x and subtract it over to the right side. Negative y equals negative 2x minus 8. I need to isolate the y, so I'm going to divide by a negative 1. Y is positive 2x plus 8. So I have a y-intercept of 8, and I'm going to write this as a whole number. This whole number already, I'm going to write it as a fraction, so I'll put it over 1. So I'm going to go up 2, right 1, up 2, right 1. And I was only able to do it once before I ran out of space, and so I'm going to continue that pattern, but I'm going to go in the opposite direction. So 2 and 1, 2 and 1, 2 and 1. So there's exactly one solution. These two lines cross each other at right angles, it kind of looks like. And the solution is left 2 up 4, so the solution is negative 2, 4. So here, a consistent system has a solution, an inconsistent system does not have a solution. So this system is consistent. And then an independent system has exactly one solution. A dependent system has infinitely many solutions. And this has exactly one, and so we're going to say independent. So this solution to the system meant that the system itself was consistent and independent. All right, I'll go ahead and do it again. So 3x minus y equals 2. I'll subtract the x over to the other side. I'll isolate y by dividing by a negative 1. So I'm going to start at negative 2 and then do a slope of positive 3, so up 3, right 1. And then I'll go ahead and find the other equation to graph. So 2y minus 6x. I'll go ahead and move the x to the right side. And divide by 2 to get the y isolated. And these two equations are identical, which means if I was to graph the second equation, it would be right on top of the first equation. And so here I would say that we have infinitely many solutions. And if you were to do a problem like this in high school, you'd probably literally just write infinitely many solutions and you would be done. But here we can actually say how to find those solutions. So I'm going to write my solution as a solution set, this kind of formal notation. This is what my math lab is looking for. And my solution set is saying any xy coordinate such that you're satisfying the equation 3x minus y equals 2, or you're satisfying the equation 2y minus 6x equals negative 4, or you're satisfying the equation y equals 3x minus 2. It doesn't matter which one you put, all of them should work, but any coordinate such that this equation is being satisfied, that's our solution. Okay, so let's go back up here. Consistent versus inconsistent. A consistent solution has at least one solution, and we have infinitely many. So we're going to say this is a consistent system. It has at least one solution. And then here, independent if it has exactly one solution, dependent if it has infinitely many solutions, which is the case here. So this is a dependent system. Okay. So this is the part that I would expect would definitely be new to you probably from this video. I believe that MyMathLab has you answer these in set notation as well. But I think that that just means that you put when the MyMathLab pops up, the squiggly brackets, you're just going to put your point inside the squiggly brackets. So somebody correct me if I'm wrong on that, and I'll have to re-record this part of the video. All right. The next solution method we have is solving by substitution. And so when you solve by substitution, that just means you're going to isolate one of the variables in one of the equations. It could be x that you isolate, it could be y that you isolate, and then you take the remaining equation and you plug it into the other equation. So here, if I look at this, I want to see which variable is closest to being isolated, and I can see that that's this y right here. It doesn't have a coefficient, and so I'm going to take this equation, 3x minus y equals 6, and sometimes you get lucky, sometimes you already have an equation where that variable is isolated, but in this case we didn't. And I'm going to isolate that y, so I'm going to move y to the right side of the equation. I'm going to take the 6 and move it to the left side of the equation. And so what I have now is y equals 3x minus 6. And now what I can do is take what I know that y equals and substitute it in for y in the second equation. So I am getting rid of a variable. 6x plus 5 times y equals negative 23. And y can be represented by 3x minus 6. And so now I'm just going to go through and solve this equation for x. So 6x plus 15x minus 30, that's 21, 21x minus 30. And then I'll go ahead and take the negative 30 and add it to the right side. 21x equals 7. And then I'll go ahead and just divide by 21. And so x is 7 divided by 21, which is 1/3. Both of those numbers are divisible by 7. So 7 divided by 7 is 1, 21 divided by 7 is 3. So to find the y coordinate, I have 3 places where I can plug this x coordinate in, and it doesn't matter which one you use. You can plug the x coordinate in the first equation and solve for y. You can plug the x coordinate in the second equation and solve for y. Or you can take this equation where you have solved for y already and just plug the x coordinate in and see what you get. And this is typically going to be your easiest method. So y equals 3 times 1/3 minus 6. 3 times 1/3 is just 1. 1 minus 6 is negative 5. And so that means our solution here is 1/3 negative 5. And then if we go through and write the words that describe this, we have a consistent system because we have at least one solution. We have an independent system because it's exactly one solution. It is not infinitely many. So this is consistent independent. All right. We're going to go ahead and do it again on this other problem. So 3x minus y equals 9. I'm going to use a very similar method here. I'm going to get the y alone by adding the y to the right side and subtracting the 9 over to the left side. So 3x minus 9 equals y. And then I'm going to take the y and substitute it into the equation for y. So 6x minus 2 times y equals negative 7. Y equals 3x minus 9. So that gives me 6x minus 6x plus 18 equals negative 7. And we get, that's just 0. We get 18 equals negative 7. And if this ever happens when you're solving a problem algebraically like this, so this is solving a problem graphically, this down here is solving a problem algebraically. If you end up with something that's not true, it means there's no solution. If we had graphed these by hand, they would have been two parallel lines. So this is no solution. And because there's no solution, we're not going to have a way to write this right here, because there is nothing that would satisfy how to write an ordered pair that would make a solution happen. There is no intersection point between the two lines if they're parallel. So here, between consistent and inconsistent, we're going to say that this is an inconsistent system because it has no solution. And then because it's inconsistent, we don't have to use one of the second terms. So I'm just going to say inconsistent, and I'm going to leave it at that. All right. We have one more method. So graphing, substitution, and then last method is called elimination. I use the term elimination in the notes because that is the most common term that I've seen to describe this method. However, your textbook calls this the addition method, and I've never seen any other textbook call it that. It's not wrong, it's just different. And if you see it anywhere outside of this textbook, you're probably going to hear it called elimination. So that's what I'm going to call it. But in the instructions, I put both, and I'll probably continue to do that anytime I write the instructions. So we're going to solve by elimination, and the goal with elimination is to line up the two sets of equations and get one of the variables to cancel each other out. And you're going to do that by having coefficients that are the same number but opposite signs. So here I could cancel the x's or cancel the y's. It doesn't matter which one I want to cancel. Some people always cancel the same variable. Usually I go with whatever one seems the easiest. So here, to cancel them, both of them look like they could become a 6, and then a positive 6 versus a negative 6. And it looks like they're going to be an equal level of difficulty, and so it truly doesn't matter. So I'm going to take the top line and multiply by 3. That'll make my x positive 6x. And then I'm going to take the bottom line and multiply by negative 2. That's going to make the x on the bottom negative 6x, and then the two lines will cancel each other out with the x's. So for the top, 3 times 2x is 6x. 3 times negative 3y is negative 9y. 3 times negative 2 is negative 6. And then for the second line, I have negative 6x, positive 4y, negative 24. And so these cancel, they eliminate, or in this case, I added them together and that made them eliminate. And then here I have negative 5y, and that equals negative 30. And then I'll divide the negative 5 over, and I get y equals 6. So just like before with substitution, it doesn't matter which equation you choose to find your other coordinate. I can take y equals 6 and plug it into the first line. I can plug it into the second line, or I could plug it into either of these lines that I multiplied by some other number. So I like to go with the one that has the smallest numbers, and so I'm going to plug it into the first line. So 2x minus 3 times y equals negative 2. 2x minus 18 equals negative 2. So I'm going to add the 18 over. 2x equals 16. So I'll divide by 2, and I get x equals 8. And so that means I just have one solution this time. My solution is 8, 6. If I remember the words, that means that I have a consistent system. There is a solution. And that system is independent because there is exactly one solution, not infinitely many. All right, let's try this again. So this one, because that first line has some fractions involved with it, it might be a little bit harder for you to think about what can cancel out. So if you want to take care of the fractions first, that's fine. So between 2 and 3, the common denominator is 6. And so I'm just going to multiply the entire equation by 6, and that's going to get rid of all my fraction coefficients. So denominators, I'm just writing this for future reference. Denominators of 2 and 3 give me a common denominator of 6. That's why I'm choosing to multiply the top line by 6. So I just want to see what happens, and then from there, if I need to change anything, I will. So I've got 6 times 1/2 is 3. 6 times negative 2/3, that would be 6 times negative 2 is negative 12. Negative 12 divided by 3 is negative 4. 6 times negative 2 is negative 12. Okay, so there's my equation. I'm going to write down my other equation. Okay, and so here, when I do this, I get 0, 0, 0. So what I just ended up with is I was solving a problem algebraically, and I got 0 equals 0. So this is very similar to the previous page, but it's a little bit different. It's similar in that I ended up with an equation at the end where my variable had disappeared. But what's different is here I ended up with numbers that did not equal each other. They were not true, and so I said there was no solution. And here I ended up with numbers that were true. If you end up with numbers that are true, it means that you have the same line. The lines are not parallel, they're the same line. So we're going to say this is a situation where we have infinitely many solutions, and we're going to say that our solution is xy, such that this equation is being satisfied, or this equation is being satisfied, or one of these equations. It doesn't matter because technically all 4 of them are the same. If you were to graph them, they would all be the exact same line. So I'm just going to write down the second one because, I don't know, that's nicer than the fraction one. So as long as you are getting points that come from this equation, then it will be a solution on the line, and it's infinitely many solutions. So here we have a consistent system because there are some solutions at least one. And then we have a dependent system because it's more than one. It's not exactly one, it's infinitely many. All right, so those are our solution methods. Of course, we're going to have some word problems with this. That's pretty common when you're working with systems. And so I want to go through 2 examples that look, a little bit different, just so you guys can see how they might look when they're set up. So first example says 2 DVDs and 3 CDs cost $78. I know none of us really buy DVDs and CDs anymore, so just pretend this is like 10 years ago and that you still bought this type of thing in physical form. One DVD and 4 CDs cost $74. What is the cost of a DVD? So the first thing you need to do is actually write down what variables you're going to use. And you can use X and Y, or you could use D and C if you wanted, that's fine. But you need to think about what the variables actually mean, because some students would look at this and they would say, one of these is the number of DVDs and the other is the number of CDs, and that would be wrong. So here, based on the way the question is phrased, the X stands for the cost of a DVD. And the other is going to be the cost of a CD. And if you're not sure how to define these, then just look at the final question, because that's going to be your hint. They're going to be asking in the final question what they want you to solve, and that's going to be basically what your variable is going to be representing. So the cost of a DVD, the cost of a CD. So 2 DVDs and 3 CDs cost $78. So 2 times the cost of a DVD plus 3 times the cost of a CD is going to be an overall cost of $78. 1 times the cost of a DVD plus 4 times the cost of a CD is going to be $74 overall. And then if they're asking us to say what the cost of a DVD is, they're basically asking what does X equal? So you have multiple methods you could use. Typically, solving by graphing is not going to work, just because if we're solving by graphing and we get a decimal answer, then we're not going to be able to tell exactly what that decimal is. So when we do systems and we're doing modeling problems or application problems, we're pretty much stuck with elimination or substitution. So I could see this problem going either way. You could isolate the x and then plug it in for the x on the other one. You could use substitution, or you could use elimination. So I'm going to go ahead and do this problem using elimination. So I'm going to take the bottom line and multiply it by -2. This is going to make it so my top line is positive 2x and my bottom line is negative 2x, and then they're going to cancel out. So I'm going to have 2x plus 3y equals 78. I'm just rewriting that first line. And the second line is going to be negative 2x minus 8y equals, 148. Is that what that is? Let me figure it out. 74 times 2, negative 148, yep. So those eliminate. We got negative 5y equals negative 70 divided by negative 5 is 14. Okay, and then to find the x value, you can take that y value and plug it into either equation. It doesn't matter. This equation, this equation, this equation, this equation. They're all going to give you the same answer. So I'm going to plug it into this one because it looks the easiest to me. So x plus 4 times 14 equals 74. 4 times 14 is 56. And then I'll go ahead and subtract the 56 to see what the x is. It is 18. So what is the cost of a DVD? Now, if I ask the question, what is the cost of a DVD, and you say x equals 18, that's confusing. I don't know what you mean. In fact, I used the variables x and y, but somebody else might have used the variables d and c. So you need to write your answer in a sentence where you're interpreting what your variable means. So I'm just going to say a DVD costs $18. All right. I'm not looking for, a super wordy sentence here, but I am looking for it to be a sentence. So I want to see a capital letter at the beginning and a period at the end, and I want it to be, like a decent sentence. If you say DVD equals $18, I'm probably going to mark you down for that, to be honest. Okay. Next example. Ruby invested a total of $100,000 in 2 mutual funds at the beginning of 2008. At the end of 2008, she lost 32% of the amount invested in the Fidelity Balanced Fund and lost 50% of the amount she invested in the Fidelity Value Fund. If her losses totaled $42,800, then how much did she invest in each fund? So I have to define my variables first. I have to think about what they equal, and it's easy to start off and just automatically say X is, what was the first one? Fidelity Balanced Fund, and Y is Fidelity Value Fund, but that doesn't tell me what about those funds. Is it how much she lost from each fund? Is it how much she invested in each fund? So we need to be specific. So if we look at the question to help us be specific, it says, how much did she invest in each fund? So if we look back and see if it makes sense, I'm going to try to write this as the amount invested in the first one, in Fidelity Balanced Fidelity Balanced Fund. And then amount invested in Fidelity Value Fund. And then we'll make sure that that makes sense as we write the equations. So she invested a total of $100,000. So the amount she invested in one fund plus the amount she invested in the other fund equals $100,000. And that would make sense. So I'm going to say X plus Y equals 100,000. Okay? The next one says she lost 32% of the amount invested in Fidelity Balanced and 50% of the amount she invested in the other one, and her losses were 42,800. So 32% of the amount invested in Fidelity Balanced Fund plus 50% of the amount invested in Fidelity Value Fund were lost, and the total number of losses was 42,800. Okay. So I have multiple ways I could do this problem, right? I can do substitution, I can do elimination, and you can do whichever method that you want. I almost always end up doing elimination on my application problems, to be honest, but I'm going to go ahead and do this a different way. So, but I will talk you through elimination if you wanted to try that. So to do elimination on this problem, I could either multiply the top equation by negative 0.32 if I wanted to eliminate the x's, or I could multiply the top equation by negative 0.50, and that would eliminate the y's. So either of those options would have been fine. Instead, I'm going to solve this problem using substitution just to show you guys another method for an application problem. So I'm going to leave the x right here, and I'm just going to subtract the y to the other side. So x is negative y plus 100,000, and then I'm going to substitute it in for the x right here. So 0.32 times x is not equal to yet. 0.32 times x plus 0.50 times y equals 42,800. Okay, and here for the x we had negative y plus 100,000 is what we had for x. And now I'm going to go ahead and distribute. So I have negative 0.32y, and then I want 32% of 100,000. 32,000 makes sense. So I'm going to combine my y's together. So negative 0.32y and 0.50y. 0.18y. And I'll subtract my 32,000 over. So I end up getting 0.18y equals, subtract 32,000, I get 10,800. And then I need to divide by 0.18. So that's 60,000. Okay, so if y is 60,000, I know that x plus y equals 100,000. And so if x plus y is 100,000 and y is 60,000, that means that x is 40,000. Okay, how much did she invest in each fund? Ruby invested 40,000 in Fidelity Balanced Fund. and 60,000 in Fidelity Value Fund.